Okay. Okay. Any more questions?
I have a question.
Yeah.
It's kind of tangentially from the midterm, but not exactly related. I was wondering if R, the set of real numbers under addition, is isomorphic to C, the set of complex numbers under addition.
No, because they have different dimensions as manifolds, right? I mean, yeah. I mean, you have a point because we know from the way that Cantor classified infinities that two different. So, for example, the positive integers z plus and the integers z, there's a one-to-one correspondence, right? So, but as groups, R1 is an additive group, and C2 is also C1 is also an additive group, right? C1 is also an additive group, and but no, they have different dimensions. So
Okay.
C1 you can it's it has you can C1 is R2, right?
Yeah.
With some extra structure put on it.
Yeah.
Right.
So this is what my intuition said, that because they have different number of real parameters, they couldn't be isomorphic. But I couldn't, because they're both uncountable. I was just forced to say they're not isomorphic because I couldn't come up with an explanation for why there wouldn't be a bijection between them. Right.
I mean, it's you can have two elements, right? You can have alpha and beta. But here you have only one parameter, right? So here you can have alpha plus alpha 1 and beta plus beta 1, and so this is a group operation in R cross R or C1. Whereas here it's gamma plus gamma 1, right? So obviously, if you take here gamma to be say so it's alpha and alpha 1, you can only create an isomorphism between this and this part. You cannot create an isomorphism simultaneously with the both parts, right?
Yeah. Later on I looked it up because I was curious, and there were some posts on Math Stack Exchange where they were saying that you can make them isomorphic to each other, but it involved some math that I wasn't is beyond me. So I was like, okay, well, I think it's fine if I just say they're not isomorphic to each other.
Yeah. What kind of what did this talk about? What technique?
They said that they're isomorphic to each other as vector spaces over the rational numbers, which I don't know what that means. I know what a vector space is, but I don't know what it means to be over the rational numbers. And then they said, since that's true, they must also be isomorphic as groups. And I also have no idea why that what links those two things. So I was like, okay, this
I see. Yeah, this is beyond our pay grade. Yeah, you're right. But that's right. So I mean, rational numbers are numbers of this form, right? And all the rational numbers apparently form a field. So when you have a vector space over a field, right? When we say V is a vector space, is a vector space over some field, say F. What we mean is that if alpha and beta are elements of the vector space, and say A and B are elements of the F, then we are only allowed to take linear combinations of this form. Okay, so you cannot take, say, so if this F is, say, the real numbers, you cannot take A to be a complex number. Okay, so So what they're saying is that this field could be just a rational number. So this field could be just, if this field is just a rational number, then the two are isomorphic, right? That's what they say.
Oh, I see. Okay.
But that's what it means for a vector. When the important thing I want you to know, take away from here, is that V is a vector space. If you come across the statement V is a vector space over some field F,
Yeah.
this is what it means.
Oh, I was thinking that this meant that alpha and beta would have to be rational numbers. And I was thinking, well, that doesn't make sense. The real numbers obviously have more numbers than just the rational numbers.
Right.
But yeah,
the thing is that a vector, we are used to thinking of vector in terms of matrices, right? So you say, oh, maybe this is a vector, or when I say a vector, you probably think of, oh, I'm thinking of a when I tell you of an n-dimensional vector space, you're thinking, okay, then we have something like this.
I was thinking of an arrow or a graph, 2D graph as vector.
Right. Well, a column, a direction in n-dimensional space, or a column vector, right? So that's just this is not a vector per se. This is a representation of a vector. Okay. I mean, it is a vector, but it's a vector in a particular basis. A vector is a more general object. A vector is a part of a set that satisfies certain axioms, the axioms of vector space. Okay, and when we introduce in that vector space, some orthonormal basis, so which means some set of basis vectors, and then which means that any vector in that vector space can be expressed as linear combination of these things. That's what it means. That's what a basis is. So when we say V is, V1, E1 plus V2, E2 plus ... Vn, En. Now these coefficients, they have to be chosen from the field. They cannot be chosen arbitrarily. So if you're considering a vector space over the reals, then these V's have to be real numbers. Okay, we cannot, if you're considering the field to be a complex numbers, they can be complex numbers. And I guess if you're thinking that they have to be rational, then they have to be rational numbers. And
I see, I get it now.
Right.
So
now
the rest of it is you have to figure out what basis you can
right. So in this basis, this guy has a representation. And that representation is V1, V2, ... Vn. But in general, this vector, and that's why, when you know this from three-dimensional vector calculus, or even just, a vector algebra, that when you change your basis, when you rotate your basis, the component of the vector changes, right? And that's why the statement that first-year undergraduates often make, that, oh, it's a positive vector, is a nonsensical statement, because whether a vector is positive, a component of a vector is positive or negative, depends on the basis you have chosen. So, for example, if I have, this is my a reference frame, and I have a vector like this, it has only one component, and that component is a positive number. But the vector remains like this, but suppose that this is my new reference frame, then the vector has, its y component is negative, its x component remains positive. In both of these cases, the vector remains unchanged, but its components are changing. And here, what we are seeing here is that this is a representation of a vector with reference to a particular, basis, right? But a vector itself is not the column. It's it is an element of an abstract set which satisfies the axioms of vector space. Now, from those axioms and some other notion of inner product, although inner product is not necessary, you can derive the notion of a basis, and then from there, linear independence. If you introduce that notion of a linear independence, then you have the notion of a basis, and from there you can derive all these things. Okay.
Yeah, got it.
So these are ideas that were supposed to be taught in your linear algebra course.
Oh yeah, they were. I just didn't know what these specific things meant.
Right. So basically, that's very good that you bring it up. That means that we are connecting the dots between different courses, right?
Yeah.
Yeah. Okay. Before we move on, any more questions?
Sir, would you check the chat, please?
Okay, so yeah, we want to come back to what is a Lie algebra, right? So we got distracted. So I think the time of break should it still be at 6, or do we have to push it back a little bit?
So 50 push it back from to 6:15 p.m.
Oh, okay, 6:15 then. Okay, we have then about 15 minutes. Okay. All right. So so we have been discussing, for Lie groups, we said that an element of Lie group that is continuously connected to the identity can be represented in this form. Okay, and we said that these xi's, these are called generators. And by the closure property, so we know that if I multiply two such elements, I should get another element like this. And then what we did is that we did a second order expansion of this. Why second order? Because we know that for abelian, for non-abelian Lie groups, if I take the left-hand side, then this multiplication in general, this is not going to be equal to I of alpha I plus beta I xi, right? In general, for Lie groups, this is not true. So, so the interesting stuff, the non-commutative stuff, comes up second order in the parameter, and we basically want to know what is the most fundamental thing that we can do to derive the condition. And we took the log of those sides and we did an expansion, and we found that for this to be true, the commutator of two of the generators should give me a linear combination of the generators themselves. And these coefficients of linear combination, which for real compact Lie groups can be chosen to be real. This is something we will show later. For now, they're just numbers. They're called structure constants. So F, I, J, K are known as structure constants. Okay, and we will show, this is on our syllabus, that for compact Lie groups, the structure constants, let me just use Fij, Fijk, can be chosen to be completely antisymmetric. Okay, so for example, so here from the definition, we see that this first two indices, it has to be antisymmetric, right? The left-hand side is antisymmetric, so the right-hand side must be antisymmetric in I and J. But there is no reason why K and J, those should be antisymmetric. But one can show that, and this will show it, that for compact Lie groups, we can write these Fijks. So for compact Lie groups, these can be written as Fijk, and that they are completely antisymmetric. Meaning that if you symmetrize all the indices, they will be 0.
So
Okay.
to clarify the continuously deformed to identity part, if I change the parameters of the matrix, if I think the matrix is on a surface, then they can continuously be deformed into the 1, 1, 1, 1 identity matrix. Is that the case?
Yeah, exactly. Yeah. When alpha is 0, yeah.
Yes, and we get the e to the power I alpha x. So those x, the generators make the Lie algebra, and the e to the power I alpha x make a group. Is that
exactly? Yeah.
So the algebra is for so that generators are from an algebra, and they are generating a set of matrices that make the Lie group.
Correct.
Oh, okay, got it.
Yes. Okay, very good.